Hello, Big Brain. For this lesson, all you have to do is get a piece of paper, and I'm going to show you an amazing proof, and all I want you to do is write down the things that I write down. And then when we're done, to show me that you followed this, just show me your proof on your paper. You can put this on a separate sheet of paper, a loose sheet of paper. You can put it in your notebook. It doesn't really matter where. I would just like you to have a copy of this proof. Okay, so push pause and get out a piece of paper, and then we will get started. All right, so let's put our name up here and what block you're in. So the proof that I'm about to show you is not fake. This is not a trick of any kind. This is a very famous proof that is pretty much going to blow your math mind. Here's what we want to try to figure out. Here's the question. What is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8? If we just keep doing that forever up to infinity, what does that add up to? And of course, it seems like, well, of course it's going to add up to infinity, but it actually doesn't. So here's how we're going to deal with this. I'm going to call this whole summation, this string of adding numbers, S. Whatever it is, whatever that answer is going to be S. Okay, so you got the idea. We're trying to figure out what S equals. If S is 1 plus 2 plus 3 to infinity. Now you can never stop. I mean, if you stop at 8 right there, we could just get out a calculator. You can't stop at 9, you can't stop at 10, you can't stop at 1,000,000, you can't stop at 10 billion. You have to stop. There's no stopping. If you never stopped adding, what does it add up to? Now I'm assuming everybody's thinking, well, it's infinity. Okay, well, let's go about it like this. I'm going to call another string of numbers S1, but I want this string of numbers to be 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 forever. So that goes on forever. And the idea is, okay, what should that be? Well, what if we just group those together? That would be 0, those would be 0, those would be 0, those would be 0, and we would get 0 plus 0 plus 0 plus 0 forever. So it looks at first glance that it's equal to 0. But the problem with that is we can group numbers in any way. Since there's an infinite amount of these ones, what if we group it like this? What if I group it as, I'll start over again, 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1. What if I group it like this, and then like this, and like this? See, negative 1 plus 1 is 0. Negative 1 plus 1 is 0, negative 1 plus 1 is 0. But see, I have this 1 in front, so now we have 1 plus 0 plus 0 plus 0 forever. Well, 1 plus a whole bunch of zeros is equal to 1. So it seems like it depends on where you start adding up the zeros is what the final answer is. Now, that doesn't make any sense. You can't really have that. You can't have, just because you started adding in a different place, end up with a different answer. So some people just say, well, let's just take the average, but that's not a very mathy kind of way to deal with it. But let's try this. What if we have 1 minus that S1 series? 1 minus all of those ones. Let's take a look at what that is. Okay, that's this one right here, minus the S1 package, which was 1 minus 1 plus 1 minus 1 plus 1, etc. Okay, well, what if I go ahead and put this negative in there? If I distribute that negative in there, so now this one was still there, so I have 1, but now I have minus 1. Put the negative in there. Now I have a negative 1, so that becomes plus 1. Put the negative in there, that's minus 1. Put the negative in there, that puts it back to plus 1 and minus 1, etc. Okay, well, can't we see that if we do all of that is just series 1? That's what it was in the very first place, 1 minus 1. So 1 minus S1 looks like it's just equal to S1. So I have 1 minus series 1 equals series 1. Okay, that's weird. It's kind of like algebra now. Just think of it like this in your head, what I'm about to do. What if we had 1 minus x equals x? See, I could just get like terms together. I'm going to add x to both sides. Okay, so I'm going to add S1 to both sides. And do the algebra on that. So those become 0. So down here, so I have a 1 left on this side of the equal sign. And on this side of the equal sign, just like over here, an x plus an x would have been 2x. Here I have a S1 plus a S1 is equal to 2 S1s. And now we can just divide off the 2 from both sides. So divide by 2, divide by 2. Those 2's go away. And we have S1 is equal to 1/2. We have a little something. Remember what S1 was? S1 was this thing up here. So I have like a mini little weird thing going on. I'm going to put this up here after this what. I now know that 1 minus 1 plus 1 minus 1 plus 1, etc. is equal to 1/2. We're going to use that later. So it ends up, it is kind of the average between this kind of method and this kind of method, but we got it with algebra. Okay, so there's an interesting little idea for what is 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1. If you do that forever, our algebra over here says that it adds up to 1/2. Okay, let's try that with something else. What if I have a second string of numbers? I'm going to call this string number 2, and this is going to be just a little bit different. I'm going to make this one 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus 7, etc. to infinity. I want to do that pattern forever. Okay, so big time math brains, think about this. And I'll tell you the specific person that came up with this proof. He's very famous. Okay, what if we're just sitting around and wondering, I wonder what S2 plus S2 would be. What if I took 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus 7 and added it to its own self? Well, let's take a look. Let's stack it up. Let's say I have S2, so that was 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus 7 minus 8, etc. And then I want to add to that another S2, but this time I'm just going to slide it over a little bit. I'm going to put the 1 right there instead. Since it goes on forever, it doesn't matter if I slide what order you add in. So 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus 7, etc. Okay, let's add that up. Okay, S2 plus S2, so that would be 2 of those S2s. Okay, 1 plus, I don't have anything there, so that's still 1. But now when I add negative 2 plus 1, I get minus 1. 3 minus 2 is positive 1. Negative 4 plus 3 is negative 1. 5 minus 4 is plus 1. Negative 6 plus 5 is minus 1. Okay, look what is happening. Plus 1, etc. Okay, we just figured out what this is. That's what I put in the cloud up here. 1 minus 1 plus 1 minus 1 plus 1 minus 1 is actually the number 1/2. Okay, so we can actually figure out what this adds up to, because now we have 2 of these S2s is equal to 1/2. Okay, that's ridiculous. I'm going to go ahead and divide by 2, or I think an easier way to divide by 2 is multiply by 1/2. So I'm going to multiply this side by a half so those 2's go away. So I'll multiply this side by a half. So it sure looks like this S2 string of numbers adds up to 1/4. So when you go to infinity, weird things happen, and you're starting to see that. We got some weird things going on here because we're trying to add numbers all the way up to infinity with never stopping. So I'm going to put this in a cloud because this one's going to be used later. 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus 7 minus 8. If we do that forever, it adds up to 1/4. Okay, now that's some backstory to try to figure out what our original question was asking. Okay, so we have some things to work with now. Okay, remember the original question? The original question was, we have this string of numbers that was 1 plus 2 plus 3 plus 4 plus 5 plus 6, etc., and we want to know what that equals. Okay, well, let's try this. Let's take the original string of numbers and subtract the S2 string of numbers that we figured out. Okay, so I'm going to write that out here. So I want to take S, which I know is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 on forever. And I would like to subtract S2, which S2 was this one right here. 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus 7 minus 8, etc. Okay, so I want to do that. Okay, so I want to take S minus S2. So that means I take the top one minus the bottom one. So 1 minus 1 is 0. 2 minus negative 2. Okay, so that's not 0. 2 subtract negative 2 actually ends up being 4. 3 subtract 3 is 0, but 4 subtract negative 4 is positive 8. 5 subtract 5 is 0, but 6 subtract negative 6 is positive 12. 7 subtract 7 is 0, but 8 subtract 8 is positive 16, and so on. Okay, over here we have S minus S2, but I already know that S2 is the same thing as 1/4, so I'm just going to put that 1/4 in there. Okay, what might we be able to do with that? So that looks a little bit weird. Okay, well, how about this? Notice that all of these are a multiple of 4. I'm going to factor out that 4. So I'm going to say S minus 1/4. I'm going to pull out the 4. Okay, 4 divided by 4 is 1. 8 divided by 4 was 2. 12 divided by 4 was 3. 16 divided by 4 is 4, and so on. But look, this is already something that we know. That whole thing is 1 plus 2 plus 3 plus 4 plus 5, which is just the original S. So let's see if I can rewrite what I've got here. I've got S minus 1/4 equals 4S. Okay, well, I can do algebra again. How about I combine I'm going to combine like terms here. How about I subtract S from both sides? Okay, subtracting S from both sides. Those are now gone, so this is negative 1/4, and this is 3S. Okay, just like we did before, I need to divide by 3, or I think an easier way to divide by 3 is multiplied by 1/3. If I multiply by 1/3, that 3 and that 3 cancel out, so I'll multiply this side over here by 1/3. So now I have S equals 1 times 1 on the top is 1, 3 times 4 on the bottom is 12 with a negative. Okay, we just did a proof on how much all of the numbers add up to, because S is 1 plus 2 plus 3 plus 4 plus 5 plus 6 forever, and it now equals negative 1/12. Okay, that's not a lie. All of the positive integers, I know that's going to blow your mind, all of the positive integers, if you never stop adding them, add up to negative 1/12. This is actually used in the beginning of string theory. String theory, one of the theories that tries to explain the universe, this is actually a statement that gets it all started, one of the statements that gets it all started. If you would like to read something about this or look it up again, this is called a Ramanujan Sum. Oh, I should have looked up how to spell Ramanujan. Okay, I'll look it up in just a second. So we want to do a Google. If you do a Google search on Ramanujan sums or sum of natural numbers. Natural numbers are the counting numbers, 1 plus 2 plus 3 plus 4. You will find this proof. In fact, Ramanujan, I'll let you look up how to spell it. If you Google Ramanujan sum, let's see, it's Ramanujan. I think it's Ramanujan. That's not quite right. It's close to that. That is a famous mathematician from India who is extremely poor. He was extremely poor, grew up in the slums of India, and created a whole bunch of really amazing math. Okay, I looked it up. I almost had it right. It's Ramanujan, Ramanujan. So he's a very famous mathematician. They made a movie about this guy a couple years ago. It's called The Man Who Knew Infinity. So that would be an interesting movie to search for. Okay, so to get credit for this, just show me that you have this in your notes somewhere or on a piece of paper that you can share, and show people who you think this would be cool. It's very interesting. It's called the Ramanujan sum. All the sum of the integers add up to negative 1/12.